All right, so we're on page 233 on your Finney Calculus textbook here. If you want to look up that in the textbook as we go along, I encourage you to do that. I do have an example that's largely worked out. I'm going to just do step by step here to outline this example. As we talk about linear approximations, I guess I usually start with the title, right? Linear. So linear is straight line. Approximations is kind of an estimation. So we're using a straight line to estimate something, all right? And before we get into what linear approximations is, what I want to do is just highlight what straight lines are like again, and how we can use slopes and points to find other points. For example, y equals mx plus b is the slope, y-intercept form of a line. And so the slope is the m value, right? That's the slope. And the b value here is the y-intercept. So we know this from years ago. This example right here, y equals 2x plus 1, is a straight line with the slope 2 and with y-intercept 1. So here's the y-intercept, 0, 1. That's the y-intercept. And the slope is 2. So if you remember in grade 9, 8, 9, we first started doing this, how you graphed this line, the best way to do this is probably to start at 0, 1, the y-intercept there, and then use the slope to map the next point. And so what you would do is you would understand that 2 is actually 2 over 1, and slope is rise, or the number of units of rise divided by run, rise over run. So we'll start at this point, we go 1, 2 units, and then we go over 1 unit. And so that's how we map the next point on that line. You can keep doing that over and over again, and so you get a lot of points, and you can connect them, and that's your straight line. Remember that? Really easy, right? So what I want to focus on is this, is that we can actually use a given point and the slope to find the next point. Well, we've done it graphically. What does that look like now using the equation? So what are some equations of a line other than y equals mx plus b? Well, if you remember, this is the point slope form. The point is the coordinate x, y, and here's the slope. So this is the point slope form, okay? Now, the equation of the line that I've given you over here, y equals 2x plus 1, can be written fairly easily in the point slope form. So if we rearrange this a little bit, the point that we're going to use here is, so we can rearrange this to y equals 1 plus 2x. We can take this 1 over to the other side, and that's y minus 1, so that looks like this part. And the 2 times x can be written as 2 times x minus 0. And so here you'll see that we have this line in this, this format. Okay? Now, what does that do? How does that help us? Well, and again, this is going somewhere, so watch closely. I have an x and a y in this equation. And I have the slope, and I have a point that's on the line here, right? 0, 1. And so if I include an x value of another point, so if I take any x value, I can put that x value right here. So let's say I want to find out what this y value is on the line with another x value. So I've got x, I've got y, and I've got x, and I'm trying to solve for y. You can see that I've got everything filled out. There's my original x, y coordinate here now. Here's my slope, and here's the x coordinate for the second point. I can solve for the y coordinate for the second point, okay? That's this coordinate right here, this y level. And so if I solve for y, I find out using the slope and using the other points that are given, I can find out that y is 3. All right, now this is a long, maybe a little bit of a complicated way of doing this. Why can't you just use the graph? Well, this is, now let's say we don't have the graph. Let's say we just have the equation. How would we do this? And again, this leads up to our lesson for today. So the 3 is actually this value right here, okay? So going from 1, we go up 2 units from 1 to 3. That makes sense, okay, to get the next point, all right? So what's the point here? What's the point, pardon the pun? Using this point slope form of a line, we can predict a y value that is on the line if we are given another x value. So we could substitute any x value here. I could substitute 2 or 3 or -5 or -7, and I could find out what the other y value is, right? I just put that new number in here, and I go ahead and evaluate. Not a problem. Okay, so what does this all mean for us? Well, when we're talking about linear approximations, what we're doing is we're talking about approximating a value for a curve, a value for another function, and we're going to use the straight tangent line to do that. Now, to set this up, let me just talk about a couple things, the first of which is called local linearity, all right? Local linearity. Now, this is a concept, if you think about this, it makes a lot of sense. But for any curve, okay, so if we have a parabola, or if we have a radical, if we have a cubic function, for any curve, if you zoom in far enough, the curve will start to look like a straight line around a certain point. So it doesn't matter how sharp the curve is, it doesn't matter where on the curve this point is, any point that we choose, if we zoom in far enough, it starts to look like a straight line, and I'll demonstrate that in a second. Okay, so I want to show you something here. So this is a curve, right? This is not a straight line, and this point right here is going to be the point in question, okay? This is our point in question. Now notice that surrounding this point, that is definitely a curve. It's not quite a local max, but there's definitely, it's part of a curvature, right, of this curve. Now, all I'm going to simply do is I'm going to simply zoom in. So watch what happens to the curve in your screen as I zoom in more and more and more, okay? Now, as I zoom in, do you notice how local linearity is evident here? This now looks, for all intents and purposes, like a straight line, okay? A straight line. Now, would it be exactly straight? No, it's not going to be exactly straight. But if I zoom in to thousands and hundreds of thousands of a unit, that is virtually a straight line in that small little area, the scope that I'm viewing. Does that make sense? Now, let me zoom back out. Let's go back to home here. Okay, ooh, there we go. Look at that curve, that's cool. Okay, let me zoom back out, and let me highlight the derivative. Let's see, nope, that's not it. Where is my derivative? Where'd it go, there it is. There's the derivative. Okay, so that is the tangent line to that point. All right, now what I'm gonna do is I'm going to zoom in, and you're gonna notice something really cool. As I zoom in, I'll hover right over the point. I don't have to go very far here. Now we are talking about, what's this, tenth, hundred, thousandth. So we're talking about this width here is like 1/10,000th of a unit. So we're zoomed in pretty close, okay? But notice that it is impossible to distinguish the blue line and the red line. It's virtually the same. Now technically, because we know the definition of a tangent, this red line that I'm graphing here only touches the graph at this one point. But virtually, the line and the graph here are virtually the same thing. There's a lot of points that are very, very close to each other surrounding the point of tangency. Okay, so what does this mean? Well, you jotted this down in your notes already, maybe, but if you haven't, there it is. This means that the function f of x, whatever it is, okay, a very sharply curved parabola or a gentle, cubic function or whatever it is, the function will approximately mimic its tangent line, or the tangent line will approximately mimic the function immediately surrounding the point of tangency. Immediately surrounding the point of tangency. And we can use this fact to approximate points on a curve if we're given the function only, like the description of the curve, and we're given a point on that curve. We can use the tangent line to estimate a point that's nearby that tangent line. Okay, so I'll say that again. We can use the tangent line to a curve to estimate or to approximate another point that's actually on the curve without actually dealing with the curve at all. If I have the equation of the curve and I pick a point on that curve, that's the point of tangency, I find the derivative, I use the equation of that derivative line, I can actually find out another point on the tangent line that is going to approximate the point on the curve. So again, I have something drawn over here on the side, so let me just highlight this for you. Again, very crudely drawn, but notice this red line is the curve. And if I were to draw a tangent line, let me see if I can draw this a little bit better. Okay, let me draw this here. So the tangent line, very crudely drawn, looks like this, right? So I can kind of tell that any points immediately surrounding the tangent line would be good approximations of the curve here. Now, if we get too far away, obviously there's more and more deviation from the curve. So the closer we can get to the tangent line, the better we can approximate the curve. Okay. All right. So we know how to find points on a straight line. We did that at the beginning of the lesson. We know how to find a straight line that touches the curve at one point. That's called a tangent line. And so I'm going to use the tangent line, the point of tangency, to find another point on that tangent line. And that is a way that we can approximate a value on the function. Okay, so here it is. This is the equation for linear approximation. Okay, and the notation that's usually used is L of x here. So that's the linear approximation. This is the equation that we're going to use. Let me just walk you through it. So similar to the example that we used before, okay, we have the approximation, and this was the y value before, right? We have a value on the curve. Okay, so that's going to be our first y value, f of a, that's on the curve. We're going to add the slope, so that's the rise over run. That's this part right here. And we're going to multiply that by x minus a. Now that is the difference in the x values. Notice that that is the run. Okay? When we simplify this expression up here, when I multiply this, I actually have my new y value, that's my approximated value that I'm going to get. We take our initial y value and we add the rise to it. That's what we're going to end up getting. So we take a y value and we add the appropriate rise, and that's going to be my next y value. Okay, so this Lx is the linearization of f of x, the linearization. So we're going to take that concept of local linearity and we are going to make that curve into a straight line for points immediately surrounding the point of tangency. It represents the approximation of a, or of a value of f of x using a point on the tangent line near the value to be estimated. That's a bit wordy, but jot that down, and that's kind of a summary of what we've been talking about so far. So I'll give you a second, half a minute to ingest that. If you have any questions, let me know. I'm going to do some examples here. I'm going to show you kind of how this works. All right, so this is just a little bit more explanation of what we talked about here. The question, obviously, the question comes up a lot of times, when is this approximation okay and when is it not okay? So how do we know when we're getting too far away from the point of tangency? Well, it depends on the function of the curve. It depends on how curvy it is right there. So we don't really know that number, like you can go 1/10 away or 100th away, or we don't really know that number, but what we do know is that something that's closer gives us a better approximation. So obviously, if we were trying to approximate a point on the red curve here, I wouldn't use this blue tangent line to approximate this point. I wouldn't say, hey, this is a good approximation of that point. It's a bit too far away. That's 4 units away. But if we're talking about a point that's like, 0.25 units away, or something like that, or 1 units away, well, that's a great approximation. That's fine. So we're talking about, tenths to hundredths, something like that. Pretty close, okay? And then that's a reasonable approximation. There is no sort of point at which the approximation starts to fail, per se. So as long as we keep it close to a point of tangent C that is known, then we can approximate this. Okay, so if I'm trying to, and again, you don't have to write this down, but let's say that this is a point that's known. This is the red graph here is y equals root x, and this is an example we're going to do here pretty soon. But y equals root x, and I know that this is a point 4, 2, right here on the red graph. So if I wanted to know, let's say what this point is, 4.5, okay? If I don't know what this value is, and let's say this is not an equation that's easy to use, or you cannot use this equation by directly plugging in the value. You want to use linearization to do that. Well, then I would know that this is my original y value, f of a, and I need to find the rise with a run of 0.5. Okay, so I'm going to go 0.5, 0.5 as my run, and I'm going to try and find the rise. Okay, and I'm going to add the rise to my initial, right here, to my initial y value. Okay, so my linear approximation is going to be 2 plus the slope of the tangent line times 0.5. Okay, that's how we're gonna do this. Let me see if I can write that down for you. So the linearization here is going to be my value 2, my initial y value, plus the slope. Okay, so that's going to be f prime, the slope of this tangent line at x equals 4, times the difference between the x values, that is the run, or that is 4.5 minus 4. Okay, that's how we're going to do that. So let's do an actual question with this then, and let's say, I think I have it right here. Okay, so example 1, right here. Let's do example 1. So just jot this down, and if you want to sketch out this diagram here below, that's great. All right, so example 1 says, without a calculator, so we can't just plug our x value of 4.26 into our given function. Without a calculator, use linear approximations to determine the square root of 4.26. Okay, and I've got a little, diagram there, obviously. So I'll give you a chance to jot that down. Okay, so how do we think about this? How do we approach this? Well, it doesn't give you an equation, right? But we are talking about the square root of a number. Okay, so the square root, I could use the equation y equals root x. Okay, that's the function that I'm going to use. And I know that 2 is the answer when I take the square root of 4. So I know that there's a point 4, 2 that's on this equation. Now we've sketched it out, I've given you the sketch. The red function is the square root function. This is y equals root x. And this is the point on the red function that we know. It is the point 4, 2. Everybody good so far? So even if you're not given an equation, it's like, well, I'm looking for the square root. So I should probably use that square root function. And I'm going to use the tangent line at a point that is nearby that I will be able to know and to calculate. So you know 4, 2, and you can find the equation of the tangent line there. All right. So if we look carefully here, what I'm trying to find, this is 1, 2, 3, 4, 5. So there's 5. So 4.26 is going to be about here somewhere. Okay, that's the point I'm trying to find, and it looks really close that the tangent line and the curve are approximately the same. So I am just going to take a slight nudge in my x value, and I'm going to try and calculate the slight nudge in the y value there. Okay, so what is my linearization formula, or the equation there? It's what, L of x. Sorry, it's gonna get, oh goodness. Okay, L of x, so we're going to go L of x equals f of a. Okay, now we'll talk about exactly what a is again here, but plus f prime of a times x minus a. All right, so what is the a value here in this question? What is the a value here in this question? Okay, so the a value is going to be the x value that's known on the graph. So a here is 4, correct? A is 4. So this is going to be a right here. So the approximation of the y value, the linear approximation, is going to be f of a, so that's going to be f of 4 plus f prime of 4 times the x value Now the x value is actually going to be 4.26, isn't it? That's what we're trying to find the square root of. So this is going to be 4.26 minus a of 4. All right, so f of 4, well, we know that f of 4 is 2, so it's going to be 2 plus, and we knew that, right? We're starting at 2, and I'm trying to find my little rise here. So the derivative of the function evaluated at 4. Okay, so this is going to take a little aside note, right? So we have y equals root x. That's actually y equals x to the 1/2. If I want to take the derivative of that, that's going to be 1/2 x to the negative 1/2, right? And so y prime evaluated at 4 is going to be 1/2 times 4 to the negative 1/2. That's going to be 1/2 over root 1/2 times 1 over root 4, or 1 over 2 root 4. That's going to be 1 over 2 times 2, or 1 over 4. Snuck that in there. Okay. All right, everybody good with that? 1 over 4. So 1 over 4. And then this is going to be the difference in our, again, this is the run, right? Think about the run. So that's going to be 0.26. Okay, so now we're getting close. Again, we don't need a calculator for this, really. 0.26 over 4. 0.26 over 4, you could write this as a fraction if you're not given a calculator at all for this, let's say, right? So this is 0.26 over 4. This 2 is actually 8 over 4. So we have 8.26 over 4. Or 1/4 times 8.26. You could leave this, if you didn't have a calculator, you could actually leave it like this. On the AP exam, you can leave your answer like this. There's less simplifications required on the AP exam, so it's not in high school as we move through. It's not a good idea to leave things unsimplified, because where do you stop for unsimplification? But on the AP exam, there's a much higher tolerance for simplification. Yep. Would either one of these be preferable? I don't know. Either one I think would be fine, technically. Now, for our intents and purposes here, you can the questions will often say to the nearest, hundredth of a to the nearest hundredth of a unit. So you can use your calculator here to simplify this to a hundredth of a unit, which I would encourage. Without your calculator, okay, this is where you're going to stop for this particular thing. But let's go ahead and use our calculator just for this calculation. You can get close, but I don't mind if you use your calculator for this. So 0.26 divided by 4. Okay, so 2.065. Let's use that whole decimal. 2.065. Okay, so that is going to be. Now what is that? What do we have there? That's L of x, right? And x, actually, we put, we could have put, included x here, 4.26 as x. So technically, I could have, maybe even arguably should have, put 4.26 here as well, okay? So I'm going to do that. To keep our notation consistent, I will do this. But this is what this is, right? It is the linear approximation of the square root of 4.26. That's what we've got, okay? So here's our answer to 3 decimal places. And I should say that when you are allowed a calculator and you're doing things to decimal places, it is 3 decimal places. That's typically the expectation for the AP exam. I'm not sure why they don't use 2 or 4, but it's 3 generally. So they will often say 3 decimal places, or to the nearest, 1,000th or whatever. So 3 decimal places is a common decimal place. So that means that this value up here, I'll do it in red as well so you can see it, but this is 2.065 according to our approximations. And if we actually now just checked to see how close we were, then we could literally just do the square root of 4 2.26. And look at this. We're pretty close. 2.06397, okay, versus 2.065. So that's a very good approximation. It's, you know, very, very close, okay? Talking about thousandths of units off. Everybody got that? Okay. All right. So your turn. Go ahead and do this question right here. Without a calculator, use linear approximations to determine the square root of 3.91. So you do this exactly the same, except, well, your A value is going to be 3.91 instead of 4.26. Okay? So go ahead and take a minute to work through that. So another way I like to write this linearization is your y value, f of a, plus the slope times the run or the change in x, right? Another way to think about that. So however you write that, that's fine. So very similar, f of 4, f prime of 4 times. Now this is going to be a negative value, right? Which makes sense because the rise should be now negative because we are going underneath our value of 2. So this rise should be negative, and we should have a value that ends up to be less than 2. Okay, so this would be your value there. Again, if you're on the AP exam doing this, I suppose this would probably be sufficient if you didn't have a calculator at all, but 2, 3, or 4 decimal places is where we go. And you could check that again against the actual calculation. Again, this is just for checking purposes, but if we did the square root of 3.91, then we have 1.97737, 1.9775. So that's very close to, that's a great approximation there. Okay, any questions about this example here? I think you got this figured out. Pretty straightforward, hopefully, not too bad. Okay, all right. I'm going to show you this. I'm going to show you this question here. Okay, this is the last one I want to go through. This adds two new things. Okay, and again, I'm going to leave the worked out solution up here so you have a little more time to just look at everything while I talk, and I'll just highlight steps as I move through. So this example is, the first part says find the linearization, okay, of f of x equals cos of x at x equals pi over 2. So first of all, the linearization is basically what we're looking for is we're looking for the expression of that tangent line, the equation of that tangent line, okay? So that we're going to be able to use that tangent line now to pick x values to find the y value, right? So we can choose any x value apart from that point of tangency. So the linearization is an equation of the tangent line necessarily, okay? And then we're going to use that equation to find cos of 1.75 without a calculator. All right, so let's go back to scratch, and our linearization equation is L of x equals f of a plus f prime of a times x minus a. The y value that we're going to be given plus the slope times the run. Okay, so we are looking at x equals pi over 2, so that's going to be our a value. Okay, so f of pi over 2, that's going to be cos of pi over 2, because that's what the f of x is. And the f prime of pi over 2, well, f prime of cos is negative sine. Okay, so that's going to be negative sine of pi over 2. Negative times the sine of pi over 2. Times x minus pi over 2. Notice we're not putting a value for x in there because I'm looking for the linearization or the equation that includes just x, a bare x variable there. All right? So, again, I don't want to go too quickly through this, but hopefully, any questions so far? Okay, f of pi over 2. So that's cos of pi over 2. What is cos of pi over 2? Well, pi over 2 is 90 degrees. Cos is going to be my first coordinate, so that's going to be 0. Moving along, f prime of pi over 2, that's going to be negative sine of pi over 2. So sine of pi over 2 is positive 1. And so negative sine of pi over 2 is negative 1. Again, don't plug an x value in yet. Let's just write the formula. So this is going to be times x minus pi over 2. When simplified, here's our linearization. Okay, so the description of how we would use the tangent line stemming from x equals pi over 2, okay, the tangent line at pi over 2 for cos x. This is the tangent line, and this is how we would use this linearization method to find a new y value. So that means I could find the linear approximation for any value that's close to pi over 2, right? So pi over 2 is about 1.65, right? 1.66. So 1.75 would be close to x equals pi over 2. So it would be reasonable to use this linearization equation to estimate my cos of 1.75, okay? So for step 1, finding linearization, any questions about this? Is this okay? Anything on the screen there that didn't make sense? Did I go too fast or no, we're good? Linearization is an equation, a general equation for that tangent line basically. Notice I haven't drawn cos of x, I haven't sketched it, we're not even sketching that yet at all. So using the linearization to calculate cos of 1.75, I simply put 1.75 in for x now that I have my equation, okay? And so the linearization, the approximation of cos of 1.75 is negative 1.75 plus pi over 2, and there you go. You could write your answer, like this. You could probably leave your answer like that in the AP exam, but simplified to 4 decimal places is negative 0.1792. Okay, and if we check that, let's see where's our mode here? Okay, that have to be in radians. Let's get out of there. So cos of 1.75, negative 0.1782. Okay, so 1792. Not too bad. Not too bad. We're in the ballpark there. Okay. Any questions about that? I'll throw that off to the side so we can see that that's our actual value. Okay, everybody good? All right, in your Finney text on page 242, there are a few questions I'll get you to work on for tomorrow, and I'll probably have something more for you to work on tomorrow on this as well. So 242, go ahead and take the remaining class time here, about 6 minutes, and start that. Finish that assignment for tomorrow, 1 to 3.